Hello, welcome back to online chemistry class. So today we'll be looking at another topic in chemistry, which is compounds of nitrogen. In my last video, I talked about nitrogen. So if you've not seen that video, kindly check through my channel to learn more about nitrogen. Okay, please, I would love to say this. Please kindly like this video, subscribe to my channel, and share my videos if you actually appreciate the content done in our video. Okay, so we'll be at the end of this lesson. We should be able to describe the laboratory preparation of some nitrogen compound, describe the haber process as industrial preparation of ammonia. Okay, so we are going to now dive into the basic concepts of compound of nitrogen. Now, did you know that there is a particular gas that can cause a kind of laughter when inhaled? Yes, there is a particular gas that if you inhale is going to cause an uncontrollable laughter, and it's called nitrogen 1 oxide. We also call it nitrous oxide. Some people call it laughing gas. Now, nitrogen 1 oxide, or what we also call nitrous oxide, is an oxide of nitrogen. Now, when we say oxide of nitrogen, it simply means when nitrogen combines with oxygen. So that's what we mean by oxide of nitrogen. So when nitrogen combines with oxygen, we say it forms an oxide. As a matter of fact, when any elements combine with oxygen, it forms an oxide. For instance, carbon combining with oxygen, that's carbon oxide. So when nitrogen also combines with oxygen, it forms nitrogen oxide. So nitrogen 1 oxide is an oxide of nitrogen and is also a compound of nitrogen. Now, what do we mean by compounds? A compound is a combination of two or more elements chemically combined together. A compound is the combination of two or more elements chemically combined together. So it simply means that if I have any two elements, for instance, hydrogen and oxygen combining together to form water, that forms a compound. Now, in this case, now I'm having nitrogen combining with oxygen to form nitrogen 1 oxide. That is also a compound. Now, because they are chemically combined, it's not easy for you to just separate them. You can't just say, okay, I want to separate the nitrogen from the oxygen. It's not easy, and that's what makes it a compound. It's different from mixture. If it's a mixture, you can easily separate the components of a mixture by maybe one separation technique or so. So I believe you now understand why what we are talking about saying compounds of nitrogen. So now we have few compounds of nitrogen actually, but we'll be talking about maybe 1 or 2 or 3 of these compounds of nitrogen. So basically we are starting with nitrogen 1 oxide. The formula is N2O. So let's talk about the laboratory preparation of nitrogen 1 oxide. This gas is prepared in the laboratory by thermal decomposition of ammonium triazonitrate 5. Now, please don't get it confused with the ammonium diazonitrate 3 used in the production of nitrogen. The one used in the production of nitrogen is ammonium diazonitrate 3, but the one used in the production of nitrogen 1 oxide is ammonium triazonitrate 5. The difference between the two is that this one is having 3 atoms of oxygen, while the diazoxide nitrate 3 used in the preparation of nitrogen contain 2 atoms of oxygen. I believe we are clear there. So please don't mix it up with the ammonium diazoxide nitrate 5 used in the preparation of nitrogen. They are 2 different compounds. Okay, now if you also see in this case now, the essence why we're having the triazoxide nitrate 5, that is the 3 atoms of oxygen, is for it to introduce oxygen to the nitrogen 1 oxide. So it simply means that oxygen is combining with nitrogen. Okay, so just like the case of the preparation of nitrogen from ammonium diazoxide nitrate 3, which we said is actually explosive and you cannot use it directly or eat it directly. The same thing applies to this ammonium triazoxide nitrate 5. It's also explosive, so you can't just eat this directly. The reaction is exothermic, which simply means it's going to release heat to the environment. So with that, you can't eat it, so it won't bring about a kind of explosion. So in other words, you are still going to follow another paths for you to generate this ammonium triazoxide nitrate 5. Okay, so now let's look at the reaction here. So if you look at the first chemical equation, we have the potassium triazoxide nitrates combining with ammonium chloride, which gives potassium chloride, and the ammonium triazoxide nitrate 5. So that means that this ammonium triazoxide nitrate 5 can then decompose to form water and the nitrogen 1 oxide. Okay, I want to believe that is clear enough. So basically, for us to be able to have this ammonium triazoxide nitrate 5, we'll be using the potassium nitrates, combining it with ammonium chloride, and to form KCl, that is potassium chloride, and the ammonium nitrate. So automatically this ammonium nitrate will decompose on its own, so yielding water and the nitrogen 1 oxide. So that's just the simple preparation of nitrogen 1 oxide in the laboratory. Now let's look at the schematic illustration as well. Okay, you can see we have preparation of dinitrogen 1 oxide. We have potassium triazoxide nitrate 5 plus ammonium chloride. This whole setup is just explaining the last part I just finished explaining. Okay, so you can see here that potassium triazoxide nitrate 5 and ammonium chloride is being combined in a round bottom flask and heated. So upon heating, it is expected that the gas will pass through this delivery tube, and the gas that will be produced, definitely first ammonium triazoxide nitrate 5 will be produced from this particular reaction we have here. So then the ammonium triazoxide nitrate 5 will now decompose to give us the nitrous oxide. Permit me to use the various name we call this particular compound. You can call it dinitrogen 1 oxide, you can call it nitrous oxide as well. Okay, so the gas is then collected over water. Now please, whenever we are collecting a gas over water, I will keep saying it that it simply means that first, that gas is either sparingly soluble in water, that is not really soluble in water, or it doesn't dissolve in water at all. Because if a gas dissolves in water, you cannot actually collect that gas over water, because that means you won't be able to have the gas. It's going to dissolve in the water. Okay, so now let's initially is N2O. Please don't mix them up so that you won't get confused. So laboratory preparation of nitrogen 2 oxide. Nitrogen 2 oxide is prepared by reacting 50% triazonitrate 5 acid with copper. Please do note that when you want to prepare this, you have to be careful. Basically, it's advisable to prepare this in a fume compound. And you should prepare it if you actually experience, because triazonitrate 5 acid is corrosive and it could be dangerous. Care must be taken while using such chemical. Okay, so now it simply means we just have to combine triazonitrate 5 acid with copper, 50% triazonitrate 5 acid. So I believe you know how to go about that preparation of 50%. If not, I might do some videos later on preparation of solution, and you can request in a comment section if you would love me to make a video on preparation of solution. So some of the nitrogen 2 oxide gas react with oxygen in the flask to form brown fumes of nitrogen 4 oxide, which is dissolved in water as the gas is passed through water. Okay, so what that means is just that as we are able to produce the nitrogen 2 oxide from reaction of triazonitrate 5 acid with copper, this part of the nitrogen 2 oxide, that is the NO, will now combine with some oxygen present in the flask, that is the flask to use in preparing the reaction. So once the oxygen combines, then that forms nitrogen 4 oxide. Nitrogen 4 oxide is actually NO2, so that tells you that more oxygen is combining with the NO to form NO2. So the nitrogen 4 oxide will now give us it comes with a brown fumes, so that tells you that even nitrogen 4 oxide, it's like it gives a brown fume color. So but the good part of it is that nitrogen 4 oxide can dissolve in water. So if you now collect the gas, that is the NO over water, the nitrogen 4 oxide, which is also produced, will be dissolved in the water, but the NO, that is nitrogen 2 oxide, will not dissolve in water. So this is a schematic illustration, a chemical equation of the reaction. So as you see, we have 3 molecules of copper combining with 8 molecules of HNO3 that we'll call the triazonitrate 5 acid. Sometimes we call it nitric acid. So it's also formed the nitrates. Water is also produced. Then we have our main product, which is the nitrogen 2 oxide. Okay, so I believe this is clear enough. Now let's look at test for nitrogen 2 oxide. Using air, the gas jar containing, it simply means you can test using air. The gas jar containing the unknown gas is open. If the gas turns reddish brown, then the gas is NO. Now you recall I said something during the production of the NO, that part of the gas will combine with oxygen to form NO2, and this NO2 is reddish brown in color. So it simply means that if you also want to test this NO, it's just for you to expose the NO, that is the nitrogen, to oxide, to oxygen the air. So if you expose it to oxygen in the air, the oxygen will combine with the NO, forming NO2, and that will gives us a reddish brown film. So that tells you that okay, the gas that is combining with oxygen is actually nitrogen to oxide. So that's if you want to test using air, that is oxygen from air. Now let's look at another method using iron 2 tetraoxosulfate 6. So iron 2 tetraoxosulfate 6 is also one of the chemical reagents in the laboratory, in chemistry laboratory precisely. A solution of iron 2 tetraoxosulfate 6 which has been acidified with little dilute H2SO4. So when we say acidified tetraoxosulfate 6, it simply means that after preparing the solution of the FeSO4, you will add little drop of H2SO4 to it, so it becomes acidified. Now this acidified solution can then be poured into the gas jar containing the unknown gas. Now the expected result is that if the gas turns dark brown, then the gas is nitrogen 2 oxide, that is NO. Okay, so that's the test for nitrogen 2 oxide. Okay, so let's check out this activity. You have been employed as a laboratory scientist. You want to distinguish between two gases suspected to be NO and N2O. Describe how you will go about it. Okay, try to attempt this. You can always go back to watch the video and get more clarification. Question 2. Provide a vivid explanation on how to prepare NO and N2O in the laboratory. So let's talk about, so you can ammonia. Actually pause this video and quickly do. The formula of ammonia is NH3, and ammonia is the only hydride of nitrogen. Ammonia is the only hydride of nitrogen. Now, what do we mean by hydride? When an hydrogen combines with another element, it forms an hydride. I repeat, when hydrogen combines with another element, it forms an hydride. So in this case now, hydrogen is combining with nitrogen to form ammonia. So let's look at the laboratory preparation of ammonia. Ammonia can be prepared in the laboratory by the reaction between calcium hydroxide, that we also called slake lime, combining with ammonium chloride. So what we are saying in essence is that if we combine calcium hydroxide with ammonium chloride, it gives calcium chloride plus water as well as ammonia. Now this ammonia that is produced can be dried using calcium oxide. Calcium oxide is actually a drying agent. However, whenever you are selecting a drying agent, you have to be sure that that drying agent that you want to use will not be reacting with the gas you want to dry. So in this case now, you cannot use H2SO4 and calcium chloride to dry ammonia, because those gases will definitely react with ammonia, so you wouldn't want that. So you must always use a drying agent that will not react with the compound or the substance you want to dry. Okay, This is a schematic illustration of the laboratory preparation of ammonia. So you can see we have ammonium chloride combining with calcium hydroxide, and it's been heated, then it's passed through this delivery tube. So here now in this jar we have calcium oxide. So the calcium oxide, the function of the calcium oxide is just to dry the gas. So as the gas passes through this calcium oxide, it's being dried by the calcium oxide, and the ammonia gas can then be collected in an inverted gas jar. Now when we say inverted, why do we have to use an inverted? This is upward delivery, actually upward delivery of the gas. The reason why we collect gas in this way, inverting a test tube or inverting a gas jar to collect a gas, is when the gas is less dense than air. Ammonia is actually less dense than air, so it's always advisable, if you want to collect such gas, to collect it by upward delivery. The logic there is that the gas will be here and the bottom part is going to be filled with air. So, but if you turn the test tube or the gas jar upright, it simply means that you are collecting by downward delivery, and by so doing, the ammonia gas will float on top of the air. So since it's a gas, it can escape to the atmosphere. But by the time you invert the gas jar or your test tube that you want to use to collect the gas, it simply means that the air will be below and the gas will be on top. So the air will serve as a shield to prevent the gas from escaping. So that's the basic reason why gas is collected in this way. And gas that are collected in this way are less dense than air. They are less dense than air, which simply means they are less heavier than air. Let me put it that way. Okay, so now I want to talk about the industrial preparation of ammonia. Industrial preparation of ammonia. So industrial preparation just simply means production in large quantity. Now, ammonia is manufactured from nitrogen and hydrogen by the haber process. So if you are asked a question, how can you prepare ammonia industrially, is by haber process. So haber is actually the name of the person, one of the person that actually discover how to produce ammonia in large scale. So in this haber process, nitrogen and hydrogen are combined together in the ratio of 1:3, that is 1 volume of nitrogen and 3 volume of hydrogen. So we have the schematic illustration here. Now you can see that the nitrogen used in the haber process is getting from air. So the nitrogen is getting from air, while the hydrogen is getting from natural gas. And the natural gas in this case is methane. Methane is a natural gas, that is getting from crude oil as well. Okay, so now this nitrogen and hydrogen is then combined in the right volume and is passed into a reactor. Now the reactor is has been constructed in such a way to be able to carry out the reaction. The temperature at which the reactor is being operated is at 400 to 450 degrees Celsius and a pressure of 200 atmospheric pressure. Then the catalyst being used is ion catalyst. Now, I need to explain this. The haber process makes use of the Chatelain's principle, and Chatelain's principle explains that at high pressure, is expected that the part of the reactant with lower volume will be favored. I will have to explain that better off when I'm showing the chemical equation for the reaction actually, but I just need you to understand that the Chatelain's principle is applicable when it comes to industrial preparation of ammonia. First, this reaction is exothermic, which simply means it will be released. So if it is going to be released, is not advisable to use a very high temperature, to work with high temperature. So you can't just say, okay, you want to go with a temperature of 600 degrees Celsius or 700 degrees Celsius. Now, at the same time, if you said, okay, let me go with a lower temperature, below 400 degrees Celsius, so that means that the reaction will be going at a very slow rate, which will not really favor the industry, because they will be spending more time to produce a particular volume of ammonia. Now, at the same time, the reason why they have to use the 200 atmospheric pressure, ATM simply means atmospheric, the 200 atmospheric pressure, actually they can use higher pressure. They can use a pressure of 800 degrees Celsius, a pressure of 200 atm, a pressure of 800 atm, a pressure of 1000 atm. But now where the problem comes in is that the plants that can withstand such high pressure is very expensive, highly expensive. So it's not economically favorable for an industry to be working with high pressure, even though they know that using high pressure will give them more yield of the ammonia, but it's not economically favorable for them. So it's better for them to now reduce the temperature as well as the pressure and still get a reasonable yield. So what we have here, the 400 to 450 degrees Celsius is the optimum temperature, while 200 atm is optimum pressure, that is a pressure that can still give them a good yield. Then they also require a catalyst, an ion catalyst. So now it is expected that not all the nitrogen and hydrogen gas will combine. So any gas that is left that is not combined, any nitrogen and hydrogen gas that is not combined, can still be recycled back and go back to the reactor, and the process will start all over again. So remember that the equation is actually a reversible reaction. So at the end, liquid ammonia is produced, and this process actually gives a 15% yield of ammonia. Now let's quickly look at the conditions necessary for industrial preparation of ammonia. First, we have finely divided ion catalyst is used, temperature of about 450 degrees Celsius is used, pressure of 1200 atm is used. Then the use is about 15% under this condition. So under this condition you get 15%. I've also talked about all this earlier. Okay, now this is a schematic illustration, and as you can see, we have hydrogen and nitrogen compressed here, Then from there it gets to the reactor. So in the reactor we have ion catalyst, so and that's where the process of ammonia takes place. Now the ammonia then gets condensed here, and that's from there you now have your liquid ammonia. So unused gas, unused hydrogen and nitrogen gas can still come back here and still be used to produce more ammonia molecule. Okay, now let's look at the equation. So as I was explaining the other time about the Le Chatelier's principle, as it is applicable to production of ammonia by haber process, it involves a reaction between nitrogen and hydrogen in the volume of 1:3 to produce 2 molecules of ammonia, and it will be lost. So it simply means that it's an exothermic reaction. Now, according to Le Chatelier's principle, increasing the pressure will favor the side of the reaction with low volume. Now, if you look at this reaction, we have two sides of the reaction. Let me call this side where we have nitrogen and hydrogen, the left side, and where we have the ammonia, the right side. Now, the Chatelier's principle says, according to that principle, increase in pressure will favor the side with the lowest volume. Now let's look at the left hand side. Nitrogen is 1 volume, hydrogen is 3 volume, that's total of 4 volume. If we look at the right hand side where we have ammonia, the total volume there is just 2, so that means we have less volume here. So increasing pressure will favor production of ammonia. So it is expected that if pressure is being increased, let's say from 200 to 300 to 400, more ammonia will be produced. Okay, so but the problem there is now the industry cannot afford to purchase a plant that can withstand a pressure that's high, like 300 atm, 400 atm, and so on. So they rather stick to the 200 atm that is economically friendly, and they'll still be able to produce a good yield. Okay, now that's how Le Chatelier's principle is used in the production of ammonia by haber process. So you can be asked to explain the application of Le Chatelier's principle in the production of ammonia. So you are relating it to pressure and volume, okay, and also temperature. Because it's an exothermic reaction, then lowering the temperature will be the best option in this case. Okay, so that's basically the industrial preparation of ammonia by haber process. And let's look at the uses of ammonia. Ammonia is used in the manufacture of triazonitrate acid and sodium triazocarbonates. 4. By the Solvay process. Liquid ammonia is also used as a refrigerant. Aqueous ammonia is also used in laundries as a solvent for removing grease and oil stains. Then we also use it in softening temporary hard water. Assignments. Discuss the physical and chemical properties of NO, N2O, and NH3. Number 2. Explain the laboratory and industrial preparation of HNO3. So that is going to be an assignment for you. Try as much as possible to attempt it. Then make sure you indicate chemical equations where necessary. So that will be all for this lesson. Please kindly like and subscribe to my channel. If you have any question, you can drop your question in the comment section. Thank you. Bye.